So again, horizontal projectile motion notes. You do have playlist 2 homework, range lab homework, and your bump assignment is due tomorrow if you're turning it in. Okay, so again, just a quick reminder about projectiles. A projectile is an object upon which the only force acting is gravity. We've already talked about projectiles because all of our objects that we talked about in playlist 1 were technically also projectiles. The only force acting on them is gravity, which means they are in free fall. Vertical acceleration is still negative 9.8 meters per second every second, or you can use that rounded value, and you will be using that rounded value unless you're doing a lab like yesterday, you'll be using negative 10. Okay, types of projectiles, we can have objects that are dropped straight down. We can have objects that are launched vertically, straight up or straight down. And we have objects that can be launched horizontally, like in our lab yesterday, where they're launched to the left or to the right, like this picture here with this cannon, or again, your lab yesterday. You can also have projectiles launched at an angle. We didn't test this yet, and we're not talking about it yet, but if you have a projectile launched at an angle, you'll have something that looks like this last image here. Okay, but all of these things would constitute a projectile that all be considered to be a projectile. The trajectory, whenever we talk about projectiles, you'll hear me use this word quite a bit. The trajectory of a projectile is the path that it takes. And it is going to end up being a curved path. It's parabolic. Focusing just on projectiles launched forward, the path of that projectile is parabolic or curved. The resultant motion is due to the horizontal and vertical motions being added together by that vector addition that we looked at the other day as well. And so you have both horizontal motion and vertical motion simultaneously creating these curved paths that we see whenever we have some amount of forward motion. Of course, if it's just up and down, it's not parabolic, it's linear. But if you have any amount of forward motion with your projectile, then you're going to also see that curved path. Okay, let's go away. So again, I highlighted the pathway there. When we talk about projectiles, you'll also hear me talk about terms like height and range. Of course, range was the title of the lab yesterday. Range is the horizontal displacement of your projectile, how far away it lands from where you launched it. Height, of course, would be the vertical displacement of your projectile, or rather you can use that vertical displacement to determine your height. In the case of something launched horizontally, the height is literally just its displacement, how far it fell from where it was launched. In the case of something launched upward at an angle, of course, you'd have to find your height here, but it would be the maximum displacement at the max height to the ground would be your height. Okay, so again, max height, y'all should be able to figure that out pretty easily. And then your range would be from where it was launched to where it lands in either case. All right, so when we talk about horizontally launched projectiles, which is our focus today, it implies that there is no initial vertical motion. Okay, we're not launching it up or down, we're launching it straight ahead, okay, just horizontally, which means that our initial velocity in the y direction, vertically, is 0. Okay, so v naught y is 0. You're going to see x and y a lot as we label directions. Think of it like the coordinate system in math, your x-axis, your y-axis. Y is vertical, x is horizontal. Only gravity acting on the object. Okay, it's the only force acting on the object. Thus, the gravitational field strength is what causes acceleration, and you will use that gravitational field strength, little g, 9.8 meters per second squared toward the ground, or again, 10. And again, the direction of that acceleration is always toward Earth's surface. So it's downward whenever you're looking at your projectiles. And so I'm going to go ahead and call downward negative. You don't have to. You can label your direction later on. We'll talk about that in our calculations. But I'm going to say that my acceleration in the y direction is little g, and I'm going to call it negative 9.8 meters per second every second. All right, so this is a video clip. It says, how does the vertical motion of these two balls compare? This is an apparatus that is very similar to what we used yesterday. It's just a lot bigger. So I'm going to show you this, but he's going to attach a ball at either end. And as I said, it's pretty much what we did yesterday. It has a spring and a post, and you pull it back. One of them sits on the end of the post. We didn't do that. We didn't use that end. And the other one, and of course, whenever you release it, it falls. The other one's going to sit there and be pressed by the peg like this. And so he's going to do them at the same time so that you can compare what's happening with these two balls vertically. So you're going to see one of them launched forward, the other one's going to drop, and it should happen at least fairly simultaneously. It's not perfect, but here you go. Okay, and so you're looking at kind of where they hit the ground, and hopefully you noticed that they hit the ground at pretty much the same time. Let's see if I can get it back. No, this is a different demonstration. I don't know exactly what moment that happened at. Here we go. Okay, so if you want to watch it again real quick, look at when they hit the ground. Okay, so they're hitting at the same time vertically. And so their vertical motions are actually the same. They have the same vertical motion, whether they are launched forward or whether they are just dropped straight down. Okay, so the horizontal motion of the launched ball does not affect the vertical motion. They are completely independent of one another. Okay, so vertically, a projectile moves exactly the same way, whether it is launched forward or dropped straight down. Okay, vertically, it would move in the same way. Of course, you have horizontal motion with one and not the other, but they are independent of one another. Okay, so, and again, it says that here. Thus, to describe a projectile's motion, horizontal motion is independent of vertical motion. Vertically, the object accelerates due to gravity. Horizontally, the objects move at constant velocity because the only force acting on them is gravity. If there are no other forces acting on them, they will move at constant speed once they are launched, or of course, the other one that was dropped straight down won't be moving at all horizontally. Thus, horizontal acceleration is 0 in either case. We do not have acceleration in the horizontal or x direction. So your acceleration in the x direction will be 0. Your acceleration in the y direction will be 10 if you're using the rounded value, or 9.8 if you're using a more precise value, but again, downward toward the surface of the earth. Comina, you should probably write some of this down. All right. So let's look at diagramming our vectors. We diagrammed vectors in our notes the other day. So here it is again. We have our cannonball being launched. And this last position, by the way, I put a note here. This is just before it hits the ground. We are only looking at this object as it's in free fall. So we're not looking at it after it hits or after it bounces or anything like that. We're just looking at it at that instant before it hits the ground. And so if I wanted to diagram my velocity vectors, I have an initial horizontal velocity. Okay, and I don't have any vertical velocity initially because it's launched directly horizontally. And that horizontal velocity will be the same every second because, as we just said, the only force acting on it is gravity, which means we're not going to have any change in the horizontal direction because there's nothing there causing it to speed up or slow down in that direction. The only thing there is gravity, and that's acting vertically. So all of these are the same length. Okay, all of my vectors are the same length because my velocities are all equal in the horizontal direction at each point. Okay, vertically, again, my initial velocity in the y direction is 0 because it's launched horizontally. However, due to that acceleration from the gravitational field strength on Earth, I know that my vertical velocity is going to increase and get faster and faster as it falls. And it will be the fastest at this instant just before it hits the ground, and my vector goes off the page. But those arrows get longer and longer as you go. And so those two things together, if you add them by vector addition, are what gives you your resultant velocity. It shows you exactly which way the cannonball is moving at that instant. It will be a diagonal line. It's also what creates the curve that you see here as it follows its pathway, its trajectory. We can also add in acceleration vectors. Again, the only acceleration I have is vertical, and it's due to gravity, and that value is not changing. So notice these vectors, just like the other day, are all the same, and I don't have any in the x direction. Again, my acceleration in the x direction is 0. You can use different colors or label them or something to make sure you know that this one's acceleration, this other one, this pink one, is velocity. So again, be able to represent those, or maybe look at a question on a test and pick the right image that's already labeled. When we talk about projectiles, mass has no effect on the motion of a projectile, and perhaps your data showed that yesterday. Hopefully it did, those of you that tested it. But just like in free fall, all objects accelerate due to gravity at the same rate. So it shouldn't matter what their masses are, and it definitely doesn't matter if you're in an actual vacuum, which is what this is showing us, an animation from a clip in a giant vacuum chamber. These are feathers in a bowling ball, and they fall together and hit at the same time when the air is removed from the room. Okay, so the mass, again, does not have an effect on an object in free fall, and therefore it doesn't have an effect on these projectiles either. Okay, whenever we're looking at free fall and the only force is gravity, that vertical motion, whether it's dropped or launched, is the same. Okay, and so it won't be affected by mass. These are the factors that affect range. Okay, so not mass, but initial height does, initial velocity does, and air resistance does. We tested the first two of these three. But your initial height, the greater your launch height, the greater your range. That should make sense if it's higher off the ground, that it will end up farther away before it hits the ground. If it is faster, you'll end up with a longer range, assuming everything else is equal in both of these cases. I didn't mean to do that. And then regarding air resistance reduces range. Okay, so especially if you have something that is going to be affected more by air resistance. I gave you guys pretty heavy metal balls to use in the lab yesterday, so there really wasn't much air resistance to consider with those. But if I had given you a ping pong ball, yeah, you're going to see a definite difference there because we can't get rid of the air in the room. But air resistance would reduce your range. Technically, if we include air resistance, we no longer have a projectile because we have now included another force. So when we're talking about it as a projectile, we are talking about in the absence of air. So again, these are different factors that affect it. One of the other ones that you guys came up with yesterday was gravitational field strength, and that would also affect it. I don't have it on my list. And again, we can't change that, but I guess if you did the test on the moon, you'd get different results. Factors affecting time. Okay, so those last ones were affecting range, factors affecting time, initial height. The greater your launch height, the greater your time. Obviously, you're higher off the ground, it's going to take longer for it to fall. But that initial horizontal velocity will not affect the time. It doesn't matter how fast the object is projected, it is still going to hit the ground at the same rate because that horizontal motion is independent of the vertical motion. Same thing with mass. Your mass will not affect your time because mass does not affect the rate at which it is falling either. Okay, so initial velocity, again, no matter how fast, how slow, it does not affect your air time. That's why the one that was dropped straight down versus the one that was projected forward, they still hit at the exact same time. The horizontal motion is independent of the vertical motion. All right, again, we're going to go back into kinematics because just like we were able to use these kinematic equations in our first unit with one-dimensional motion, we get to use them in this unit as well with two-dimensional motion. So this is all our review from last unit. But it says we'll be calculating for different variables related to moving objects. Again, these all should look familiar to you. You'll see average velocity, displacement, time, acceleration, initial velocity, final velocity, initial position, final position. And those are going to show up in our equations as well. The steps for solving a kinematic equation have not changed. Step one is still the same. Define and label your positive direction. Do you want the ground to be the positive direction, going toward the ground, or do you want to call that negative? Okay, and so you get to choose it. By convention, typically I think of up as positive, down as negative, but again, if you define it differently, consistently. So long as you are consistent, you are okay. You're going to use a grid or a sentence or axes in order to label your positive direction. Then you're going to indicate in words what portion of the motion you are considering. Okay, are you looking at just the first couple seconds? Are you looking at the entire thing from when it's launched to when it hits the ground? What is the question asking you to focus on specifically? And is it just one object? Are there multiple objects? Okay, so what are you considering? What time segment? What type of motion? Whatever else. Is it just horizontal? Is it just vertical? Those types of questions. The third step is to fill out a chart of the 6 kinematic variables. Again, all of these steps should look familiar. And include direction and units so you can see any discrepancies before doing math. You'll notice I have a little note though that makes this different than last unit. Now you have to include 2 separate tables because I've told you 3 times now, vertical motion is independent of horizontal motion. So you're going to have a table for your vertical motion and a different table for your horizontal motion. Okay, so you're going to label these variables in each direction separately in 2 different tables. Okay, and I'll show you what I mean in a second. And then you're going to pick the appropriate equation that you need in order to find the answer based on the variables you've labeled and based on what the question is asking you to find. They're the same equations that we've been using. They're the same first 3 on your formula chart. And of course, this 4th one's not there, but you can memorize it if you would like to use it. Okay, so here's what my table looks like. Okay, so here's my horizontal section, here's my vertical section. So for a horizontal launch, I'm going to make a table that looks like this. I have all my variables, x naught, x, v naught, v, a, and t, and I'm labeling them separately for the horizontal direction and the vertical direction. You'll notice I already have a few things filled into my table. And I would recommend that you do this on your questions as well. For the horizontal position, I'm going to go ahead and call my initial position 0. That way, if I launch something forward, my range will just be where it lands. Okay, if it lands 20 centimeters away, now I've got my range is 20 centimeters. So to make it easier on myself, I'm going to call the initial position 0 so I can measure from where I'm at to where it lands. My horizontal acceleration is also already filled in because there is no horizontal acceleration. The only force acting on a projectile is gravity, and gravity is vertical. Okay, so I have a 0 here. The other thing I have in here because of this, because my acceleration is 0, I don't need V naught and V. It's just they're the same. V naught equals V, V equals V naught. It's the same value because the velocity isn't changing. Okay, so whatever you're given, you don't have to find an initial and a final. It's that value the whole time horizontally. The other thing you'll see on my vertical side is I have labeled my final position 0. I'm going to call the ground 0. Okay, so if I'm launching something from a height of, half a meter, then I would call my initial vertical position 0.5 meters. Again, you don't have to do this, but I would recommend it. Okay, so again, I'm going to call the ground 0 vertically. And then the other value you see here is my acceleration. My vertical acceleration is due to gravity, so I have my negative 10 meters per second squared already filled in. Okay, so that's the table. Once you read the question, you can fill in the rest of it. Okay, but that's what I would start with. And this is for a horizontal launch. The other thing I want to point out to you, time is scalar. It does not have direction. There is no such thing as horizontal time and vertical time. Whatever you get for time for one is the same as it is for the other. Okay, so your times will be the same vertically as they are horizontally. Whenever you calculate it, it's the same value for both. All right, so let's look at an example. You'll notice I have my table here and I've filled some things into it already. The example says a car slides off a flat road atop a mountain, falling into deep snow. The car lands 43.9 meters below and 87.7 meters beyond the road's edge. And I have 3 questions here that I'm asking you to answer. How long did it take the car to fall? How fast was the car going when it left the road? And what is the speed of the car right before impact? Okay, I'm going to give you guys a moment to, first of all, copy down whatever you need for this, but secondly, see if you can fill in some of the table there for horizontal and vertical, whatever you think you know, see if you can fill it in. Use pencil just in case. Okay, and then we'll see what you have versus what I have, and then you can copy it down as we go through the example. All right, so let me just ask you guys, looking at this question, I see a couple numbers up here, 43.9 meters below. Where do you think I'm going to put this value? I heard vertical. Vertical what? I'm going to call that my vertical position, right? I've drawn a picture here to help you see it. Okay, but if I call the ground 0, then that means the height of this road was 43.9 meters. So I'm going to call my, oh, sorry, I forgot to do the rest of this. Let's do this first. Okay, I'm going to call up the positive direction and right the positive direction. There's my positive direction labeled. Okay, the portion of the motion I'm looking at is just the free fall stuff. I don't care about it until it's in the air, right after it leaves the road to the point just before impact. Okay, so we're only examining it while it's in free fall. Okay, so now back to this. My initial vertical position is 43.9 meters. Okay, so that is how high I was before I went off the roadway. My final vertical position is 0, so my change in position vertically will end up being negative 43.9 meters if I ask you for your displacement. Okay, so again, we fill that in. This other number, 87.7 meters, what is that? That's the horizontal position. That's where it lands. That's my range. Again, this is why we call our initial horizontal 0, because then I can just put that number here, 87.7 meters. That's going to be my final horizontal position. Okay, so again, make sure you're filling in the right side, the correct side of the chart. Okay, all right, so those are the only numbers that I see in the question. So looking at what I have here, I've got 3 things I'm trying to answer. I'm going to start with the first one. How long did it take the car to fall? I'm looking for a time. Okay, and I have quite a bit of information here on the vertical side of my table, but I'm trying to find a time. And that's a good thing to start with because it's the same for both sides of the table. If you find time, it gives you a lot of information that you can use for both of them anyway. Okay, so we're going to solve for time. Here are my equations. Okay, looking at the information I have, I don't have enough information on the horizontal side of my table to solve for time. Okay, but I do have enough over here. And if I look at the information I have x naught, x, v naught, and a. I can find time using this equation, the middle one. X equals x naught plus v naught t plus 1/2 at squared. I can find time with that equation. And so that's what we're going to do. Okay, we're going to use this equation right here. It's printed at the top if you haven't copied it yet. And we're going to rearrange it to solve for time. Now, the first thing I'm going to do is V naught is 0. So V naught times T will also be 0. I'm just going to go ahead and cross that off. And I'm going to rearrange this equation to isolate T and get T by itself. So right now I have this. If I want to get time by itself, I need to subtract x naught from both sides. And now I have x minus x naught equals 1/2 at squared. And now I have to get the 1/2 and the a out of there. So let's divide both sides by, I just put 0.5 instead because it's easier to type. Dividing both sides by 0.5a, or if you want, you can multiply by 2 and divide by a, same thing. Okay, and so I have this. Okay, but again, I want t, not t squared, so I have the square root of both sides. So the square root of 2 times x minus x naught over a, I did put the 2 here instead of the 0.5, either way, equals the square root of t squared. Okay, and of course that gives me this. So now I have an equation that I can plug into in order to solve for my time. Okay, so we're going to substitute into this equation. And when I substitute in, I have this. Again, this 2 is multiplied by this entire fraction. So just keep that in mind. But I have 2 times 0 minus 43.9 over negative 10. And all of that under my radical equals t. This becomes 2 times negative 43.9. 2 times that number is negative 87.8 divided by 10. Which is, of course, the square root of 8.78. My negative went away. That's a good thing. And I can take the square root of that number to get my time as 2.96 seconds. Does anybody have a question? I saw At least one of you got it right. Questions about this? Okay. You have to be able to do that step first because now you have enough information. You'll notice I filled it in on both sides of my chart. Now I can find some stuff over here because before I didn't have enough information to find anything out about the horizontal motion. And I need that in order to answer some of these questions like this one. How fast was the car going when it left the road? Well, it left the road horizontally. And so I need to find out what my initial horizontal velocity was. And since I don't have any acceleration horizontally, technically that's also my final horizontal velocity. But if I'm trying to solve for velocity with this information, again, I need the horizontal. I don't want vertical because it wants to know how fast when it left the road. And it left the road by sliding off horizontally. I need to look at my information and see what I can use to solve for one of my velocities over here. Okay, so again, I'm looking for my initial velocity, but you can only use the horizontal data to solve for the horizontal side of the table. Same thing's true of the other side. You can only use the vertical numbers if you're solving for the vertical side. Okay, so I'm only going to pull from these values. If I want to solve for my velocity, again, I can use this equation here. X equals X naught. I have both of those plus V naught T. I'm looking for V naught plus 1/2 AT squared. Perfect. Okay, and so we can substitute in to this. Again, you'll notice this whole end piece of my equation is going to go away because my acceleration is 0. I don't have any acceleration. So 1/2 AT squared, that's all 0. Okay, so I went ahead and just crossed it off. And now we can substitute in to this equation. This, by the way, is the other equation that I told you you could memorize. All you have to do is cross off 1/2 AT squared. It's a little rearranged, but it's the same thing. Okay, X equals X naught plus V naught T. Again, I need to get V naught by itself. So let's go ahead and rearrange this by subtracting X naught from both sides. We have X minus X naught equals V naught T. And now we're going to divide both sides by time. And look at that. Wouldn't you know, your equation is velocity equals displacement over time. Which again, we probably didn't have to do all of that rearranging to figure that one out. Okay, because hopefully you already know that equation. Again, since the initial and final velocities are the same, this is technically average velocities equal to this. All right, so X minus X naught over T equals V naught. Let's go ahead and substitute in. That is 87.7 minus 0 over 2.96. And that will give me a velocity of 29.63 meters per second. And it is my initial velocity, but it's also my final velocity because, again, it's constant velocity. There is 0 acceleration in the horizontal direction. Does anybody have a question about that stuff? As this is usually one of the trickier units for students, since you have to deal with everything in 2 different directions. Okay. Last question we had is, what was the speed of the car right before impact? I know how fast it was going horizontally, but I also know that the car was falling. So I know that it's going to have some vertical velocity as well. Okay, if I want to answer the question, what speed was it going just before impact, I'm not actually asking for just the horizontal or for just the vertical. I'm asking for the resultant of the two, which means I need both of them so that I can solve for my resultant. Do you have a question? Okay. All right, so let's go ahead. We need to find this velocity on that vertical side. And again, if I'm solving for something on the vertical side, I only get to use values from this side. I'm going to use the first equation. It's the easiest one to use for this. You could use this one, but again, this is easier. V equals V naught plus A times T. I don't need to rearrange it. It's already set equal to V. So let's go ahead and substitute in 0 plus negative 10 times 2.96. is just negative 29.6 meters per second. Okay, so now I have my vertical velocity. But that's not the question. The question doesn't say what is the vertical speed of the car or vertical velocity of the car. It says what is the speed. It doesn't want just that. Okay, that isn't the speed just before impact. That's just the vertical speed. It is moving diagonally. It is moving both horizontally and vertically. This is not drawn to scale, obviously, okay, but we're going to go with it. But I have both vertical and horizontal motion. How do I find this? Pythagorean theorem. A squared plus B squared equals C squared. 29.63 squared plus 29.6 squared equals C squared. That's that number. I'm going to take the square root of it. And we get a resultant velocity of 41.88 meters per second. That is your answer. Okay, so if I ask you for speed, don't give me the horizontal or the vertical. Give me the resultant. Does anybody have a question about this? Okay. All right, guys, for the remainder of the class period, you can work on your bump assignment. You can work on playlist 2. You can work on your range lab. Test corrections, we only have 10 minutes, so I don't know how much you can get done. Don't forget your catapult project begins on Tuesday. Okay, so make sure that you bring materials to class if you're planning on building in class. Some of you hopefully have already started building outside of class. If not, bring your stuff to class to build in class. If you haven't had that discussion yet, please start talking to your group so that you can start figuring out exactly what you're going to do. If you have any questions as you're working, please let me know.